If you've built on Ethereum, there is a good chance someone has told you this at some point. Why don't you just move to Polygon? It's the same EVM and it's way cheaper. And on the surface, yeah, that advice isn't wrong. You're still writing Solidity, using the same libraries and deploying contracts that look almost identical. What usually gets missed is what Polygon actually changes under the hood. Most teams treat it like a faster version of Ethereum, and that works fine in the beginning. The problems only start to show up later once real users are involved and the system needs to behave consistently under load. What's interesting is that this is happening at a time when throughput isn't really the bottleneck anymore. Polygon processes tens of millions of transactions per day, and Layer 2s collectively handle more than half of all EVM activity, so scale itself isn't the issue. The issue is understanding roles. Hey, I'm Steve, and welcome to the EVM world. This is a series where we break down how EVM systems actually work in production without oversimplifying the trade-offs or pushing a narrative. By the end of this video, you should be able to make clearer architectural decisions, specifically when Ethereum mainnet is doing exactly what you want, when Polygon is the better fit, and how real applications end up using both together. We'll walk through three things. First, what Ethereum and Polygon are really optimized for. Second, how execution actually differs between them. And finally, a practical demo showing how teams automate workflows across both layers. Ethereum and Polygon is to stop seeing them as competing chains and start seeing them as layers with different responsibilities. Ethereum mainnet is layer 1, and its primary job is to be the source of truth, designed to maximize security and decentralization, even if that means sacrificing speed. And that's why Ethereum mainnet still averages around 15 transactions per second. Once something is finalized on Ethereum, reversing it is extremely difficult. Polygon exists to solve a different problem. Its focus is execution at scale. Polygon keeps Ethereum's execution model, the EVM, Solidity, and transaction semantics, but changes where executions happen and how often Ethereum is directly involved. That difference is what enables higher throughput and lower fees. On Ethereum mainnet, transactions enter a shared mempool. Validators agree on ordering and execution, and finality happen together. It's slow, but it is extremely robust. On Polygon, execution looks different. Transactions are processed much faster, blocks are produced more frequently, and validation is handled by a smaller, more coordinated set of validators. This is why Polygon can sustain 60 to 70 transactions per second, with peak days going higher. Over the last year, it has processed billions of transactions, volumes that wouldn't be feasible directly on layer 1. Ethereum doesn't see every Polygon transaction. Instead, it sees summaries and checkpoints that are periodically posted back. Polygon isn't skipping security, it's inheriting it differently. The EVM stays the same, but the execution path changes, and that comes with different assumptions. Now, let's make this concrete with a real use case. Imagine a reward system where customers earn reward points by spending at outlets over time. These reward earning transactions happen very frequently, so they're managed on Polygon in a reward contract. But when a user wants to redeem those points, something that actually affects value, well, that's a critical operation. For that, we want to rely on Ethereum as the settlement layer using a redemption approval process. So now we have two chains involved, Polygon for frequent low-cost interactions and Ethereum for critical approvals. The challenge is automating this workflow so that when a user places a redemption request on Polygon, it gets validated on Ethereum, and once approved, the redemption is finalized back on Polygon. This is where Kwala comes in. The first part of the workflow listens to events on Polygon Alloy. Here, we configure Kwala to listen to specific contract addresses and an event emitted when a user locks reward points for redemption. Since this is a continuous process, the workflow is set up with a recurring configuration. When this event fires, the action we take is to call a smart contract on Ethereum. Specifically, we call the approve redemption function and pass the user's address and the amount dynamically from the event data. Once this approval happens, the Ethereum contract emits another event called redeem approved. That Ethereum event becomes the trigger for the second part of the workflow. It then listens to the redeem approved event on Ethereum. When it fires, Kwala automatically calls a finalization function back on the Polygon contract, completing the redemption process. This way, both chains stay in sync without any custom listener code or backend glue. Okay, so now let's see this in action. I'll start by simulating a customer earning rewards using a valid wallet address and earning 300 points. I confirm the transaction in MetaMask. Next, the user places a redemption request for the same 300 points. I submit and confirm that transaction as well. Once confirmed, we can check Kwala's execution logs. You can see that the approval action on Ethereum has been triggered, followed by a notification for verification. A short time later, the finalization step runs automatically on Polygon. If we check the user's balance now, it shows 0, confirming that the redemption has been completed. We can also see the approval transaction on Sepolia with the correct amount and wallet address. All of this happens automatically, driven by events across two chains. This is what modern EVM architecture looks like in practice. Ethereum and Polygon aren't competitors. They're parts of the same system, optimized for different responsibilities. The teams that do well are the ones that design with both layers in mind and automate the coordination between them. If this was helpful, feel free to subscribe and stay tuned. Thanks for watching, and I'll see you in the next one.